Welcome to the last unit of the year. So we're moving into the gas laws unit now. Just the general summary is that we're going to be analyzing gas laws and to explain the behavior of gases. We're still going to go through and calculate things like the amount of particles and, change conditions like the temperature, pressure, and then just see what results, what properties arise and so forth. Okay, and then we'll still be going through, and there's going to be a stoichiometry section as well in this unit. We're going to be going through and constantly solving some problems and so forth. So we're going to start off today with just kind of developing the main law that we're going to analyze. But before we get there, I just want to point out, okay, so we're going to look at temperature and then move into the laws there. So in general, when you guys go and measure various temperatures and so forth, we use the Celsius scale. I know, we also, like the Americans use Fahrenheit and so forth, and I think sometimes you guys use Fahrenheit as well. But so in general, we use these scales right now to measure just everyday life things and so forth, okay? So what some chemists did in the past, they were analyzing various gases. So if you took the same amount of gas and the same pressure, and they were basically they were analyzing, okay, if we adjusted the temperature, what happens to the volume of the gas? Okay, so again, think of if you're adding heat, right? So if you're adding heat to this gas here, so this is the solid, right? The liquids and the gases are further apart, they have more energy. So if you add even more energy to these gas particles here, they'll move even faster and further apart. Okay, so if they're moving further apart, you're going to get an increase in the volume. So you're noticing here, as you increase the temperature, yes, the volume is going up for these different gases, whatever they are, okay? All right, but they were also looking at, okay, well, if we start to cool down, going the other way along the scale, they were noticing that, at some point, though, when you cool a gas down enough, that it'll go to liquid phase. But they were just, analyzing this data, and they noticed that if they extrapolated, so again, they took the data that they had, and they just kind of kept drawing a line that extended past the data, they noticed that all of the gas volumes extrapolated to this value here, negative 273. Okay, so this is like the theoretical, if you had, if you got the temperature really, 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 really low, then the volume of gas, like the gases would come closer together. They wouldn't be moving as much. And so this is like the theoretical volume of zero. Okay, so theoretical. Anyway, so they noticed this, and then they were realizing that, gases, have different properties and so forth. And it's important to analyze at these different temperatures and so forth. Okay, but so in short and summary, they noticed that whenever they're using temperature in degrees Celsius, they were having to use a lot of negative numbers for temperature, and it's a little awkward when you're trying to report that temperature and so forth. So they developed a Kelvin scale. So that's what's down here. So instead of reporting lots of negative numbers and so forth for the temperatures, this corrected it, and so that you're always reporting a positive number. If you take a look here, right, so the volume pretty much goes to zero theoretically at negative 273. So they decided to set this as the zero, kind of the starting temperature of all gases, and then they just go up from there, so that you're always reporting and working with positive numbers here. Okay, so where if we kept it as a degree Celsius, which is something we use in everyday life, it just this scale here ends up, always like you're having to use lots of negative numbers and so forth. So that's what we're going to do throughout this unit. Is anytime we have a temperature that is in degrees Celsius, we're going to convert it to kelvins before we start using it. Okay, so if you take a look here, this is what you're going to do. Every time you have a temperature in degrees Celsius, you're just going to add 273.15. Okay, so that's kind of like the conversion factor, because again, this is what they noticed at negative 273.15. that's where the volume was 0. So from there, if we that's like the starting temperature to analyze gases with. Okay, so just keep that in mind as we go through the questions, to always convert your temperature to kelvins, okay? Okay, let's get some practice in actually making these conversions. So here's the first example here. So we have the standard ambient temperature. So ambient means surrounding. Temperature is defined as 25 degrees. Can you convert this to absolute temperature? Okay, so absolute temperature is the Kelvin unit. Okay, so what you're going to do here is you're going to take your 25 degrees Celsius, okay, and you're going to add our magic number 273.15. Okay, so when you add that up, you will end up with a value in kelvins. Okay, and so that will be 298.15, and then write kelvins. So you're going to find that this number is used a lot because a lot of the word problems, just things that we'll study, will have a temperature of 25 degrees, and so then you just have to make this quick conversion, and to the point that you'll just get it memorized. You're like, oh, 25 degrees, all right, 298.15 kelvins, okay? So, and use all the digits here, okay, to get a better accurate result. Okay, what if you had to convert it back to degrees Celsius? Okay, so what would you do here? Okay, so this is in kelvins, so again, you just do the opposite. So if you are adding 273 to get to kelvins, you're going to subtract it to get back to Celsius, degrees Celsius. Okay, so again, hopefully you are confident now at entering that scientific notation value into your calculator. So when you subtract it out, you end up with a very negative degrees Celsius value, okay? All right, so again, if you wanted to just kind of compare the degrees Celsius to kelvins here, here's a nice picture here. So again, 100 degrees is the boiling point of water, okay? So that's equivalent to 373 kelvins. The melting point, okay? So basically, or where, think of it as where water freezes, is 273, okay? Positive though, okay? These are positive values. And again, so if we're looking at like, you know, negative 78 degrees, so again, if it was that cold outside, we wouldn't survive, okay? So yeah, like sometimes I know some winters it gets to like negative 40, okay? But anyway, so that is equivalent to 195 Kelvin. So so hopefully you're starting to see as you drop below 273, you're getting into the negatives for degrees Celsius. It's quite cold, right? And then, yeah, if you could reach a theoretical volume of 0, you would have 0 kelvins here, okay? And therefore, it would be negative 273 degrees Celsius. Okay, so now that we can convert our degrees Celsius temperatures into kelvins, we can kind of move into the gas laws now. Yeah, sometimes I call this unit the gas laws, plural. And the reason why is because that there are lots of different laws here. I'm actually just going to fast forward and go right to the combined gas law. So if you wanted to, like we don't have time, but if you wanted to go through on your own and look up these different laws here, so basically these are the different scientists that kind of did their own studies and, figured out the volume and temperature relationship with the gas, the pressure volume for Boyle's law here, and then, pressure temperature for this one here, and then, making these constant and so forth. So anyway, there's a lot of studies that went into developing the combined gas law. So just if you wanted to look at these individually, you can, okay? All right, so we'll just jump right to the equation here. So again, I'm just saying that, yes, we used all three of these methods here in order to develop this combined gas law, okay? So if you take a look, it looks like the dilution formula, right? There's a lot of stuff going on here. So there's the initial, like think of the 1 as being initial, and then 2 as being kind of after final values and so forth, okay? So P represents pressure, V is volume, T is temperature, okay? Okay, so the units for these, so pressure will, you'll find that it will be in kilopascals. Okay, so pressure, okay, the units will be kilopascals. So again, if you're trying to okay, like that. And temperature will be in kelvins. Okay, and volume will be in liters. Okay, it's okay. Yeah, if volume was in milliliters, I guess, because it would cancel out and so forth. But I want you to just keep converting it over to liters because when we learn there's another gas law after this. It needs to be in liters because there's a constant that's in liters anyway. So just get in the habit of just switching it over to liters, okay? So if it's reported as milliliters, just convert it over by dividing by 1,000. Okay, so now that we have our 3 units here, and we have the equation here, again, here's just a picture to show you that these 3 scientists, and I'm sure people that also helped them, worked individually on these different experiments, but then we were able to just combine them in one equation. And again, like any problems that you might have with just Charles' law and so forth, you can use this equation and it'll work over here, okay? All right, so there's other things that will keep popping up throughout this unit so you need to understand what they are. So there's STP and SATP, okay? So STP is standard temperature and pressure. So basically the temperature is 0 degrees Celsius, okay? Or again, you're going to change that to kelvins by adding 273. And pressure is 101.325 kilopascals. Okay, so you want to make sure that you are, I guess I should probably capitalize pascals here. So just, yeah, make sure that you're keeping all these digits and so forth. And if it says, here's a word problem and it's at STP, okay, so it's just literally, you should know, oh, that means it's these 2 conditions here, okay. I will always provide them to you on a sheet if, actually they're on your formula sheet as well, if you look at the back for STP. All right, SATP is not on the back, but so you just need to make an adjustment here. So, so this is kind of the conditions that you would have in a lab, okay? So these are the standard temperatures, but this is considered to be standard ambient temperature. So ambient means surrounding temperature. So you have about 25 degrees Celsius here, and then we have 100 kilopascals for the pressure, okay? So anytime you see these pop up, word problems, make sure you know, oh, okay, that means there's also this additional information that I am given, okay? Okay, and kilopascals, you don't have to capitalize the pascal, it's someone's name, so, but anyway, they'll have it both ways, lowercase, uppercase, so anyway. All right, so let's move on to an example here. So we're going to use our GRASS steps here, and again, you can still use, I believe you can still use unit analysis method. Okay, so we're going to use our graphs to gather up all the information. We're going to have a lot of information compared to normal, like we have a lot of numbers to calculate with and so forth, okay? So you want to go through, again, you need to get comfortable with the different units. So pressure is kilopascals. Kelvin, right? And it's not degrees Celsius anymore, so it's Kelvin is the temperature, right? And it's not the same. It's a capital K here. It's a lowercase k here. And then volume is liters. Okay, so we're going to read through the problem, gather up all the things that are given, and then figure out what it is we need to find, okay? So we have a sample of carbon dioxide gas. It occupies a volume. So we have a volume of 25 liters, okay? And when the pressure is 125 kilopascals, okay? And the temperature is 25 degrees Celsius. Okay, so you're going to have a lot of scenarios where this is where you started with the gas. Then you did this to the gas. Okay, so it's like this could be like the before. And then now we're going to do something to it after. Okay, so okay, now I want you to calculate the volume. So you need to calculate the volume. Okay, so we're going to do our given and required steps right now. Okay, we need to calculate the volume occupied by the same quantity. So quantity, remember, is N. So it's saying that it's the same quantity. We're not going to add more gas particles, okay? All right, so yeah, that was one thing I forgot to point out here. So we have, you know, pressure, volume, temperature changing, but the amount is constant. We're not changing the amount, okay? So we'll look at a different gas law if we're going to change the amount. For today, we just assume we start with this certain amount of gas, and then we don't change it. We just kind of change the conditions and we see what happens, okay? All right, so before we got that, after, all right, so same, okay, but we're at STP now, okay, STP. Okay, so that's the standard temperature and pressure. So if we were to write those in now, so what was STP again? So if we're going back up here, STP was the temperature was 0 degrees Celsius and the pressure was 101.325 kilopascals. Okay, all right, so, so again, we have a problem here where we're given our initial values here. So think of it as like that's 1, that's 1, that's 1. Those are the initial values. And then we change the conditions. So, so now I took the pressure and I changed it to 101.325. I changed the temperature to 0 degrees Celsius. Okay, so now what happens to the volume when I make those changes? That's what we have to find. So think of this as the initial, and then these are the second, the new temperature, pressure, and volume. Okay, so we have to figure out this new volume. So what's our plan here? We need to figure out, we're going to use the combined gas law. Okay, so we're going to write that out. Okay, so we always have temperature at the bottom, and then it's PV at the top. Okay, so pressure times volume divided by temperature equals pressure times volume divided by the temperature. Okay. All right. So now we're going to go through. So we have our action plan. There's our equation. Now we're going to go through and plug everything in and solve it. So again, if you want to, before you plug everything in, I know some of you like to plug stuff in and solve it after, but if you prefer to just solve it now before, yeah, all the numbers are in there, you can do that. So before we get to solving, so we want to solve for V2, okay? We want V2. So I'm going to move, you know, the temperature out of there first, okay? So see how it's divided. So I'm going to multiply it here, okay? So P1, V1, I'm going to multiply the temperature to the top. Okay, so it was divided, so I moved it out of there. I multiplied to the top now. Okay, again, I want V2 by itself, so let's move the P2 out of here. Okay, so see how it's multiplied right now? So I'm going to divide it away. And when I divide it away, it just goes to the bottom here. Oops, and then, sorry, the temperature is still there. Temperature 1, pressure 2. Okay, so yeah, if you want to rearrange the equation before you go through and plug all the numbers in, you can. Otherwise, some people like to plug all the numbers in, clean it up, calculate it out, and then just do a few solving steps, and then you get to your V2, okay? All right, be careful too when you're writing these out that you don't write 1 where it's supposed to be a 2 and a 2 where there's supposed to be a 1, okay? Because again, something specific is going into where all these letters are going, okay? So if you are not placing things into the right spot, it's just, you're wasting your time and you're gonna get the wrong answer, okay? So just be careful. Okay, so we'll go through and fill these in. So we have P1, which is 125 kilopascals. V1 is 25 liters. T2, oh, okay, before we get to adding those in, let's convert these to kelvins. Okay, so remember add 273.15. So again, sorry, I should have got you to change this over right away before we start the problem. So just get in the habit, do that right away, and convert these over. Okay, so there's that one. And if I add 273.15 here, I get 273.15 kelvins here. Okay. All right, so I need to put in temperature 2 here. All right, and then I'm going to divide all of this by temperature 1 and pressure 2. kilopascals. Okay, all right, so from there you can see that the units cancel out nicely. The kilopascals goes, the kelvins go, okay? And then you should be getting the volume unit left over, okay? So again, this was all equal to V of 2 here. Okay, so let's go through. Okay, so again, these are nice and straightforward. It's just if you're careful, you'll get to the right answer. If you kind of fall asleep halfway through all those calculations, then yeah, you'll have a problem. So just be careful, double check your work. Okay, so we get to some values like that. Now I'm just checking my significant digits here. I had 3 here, I have 3 here, 3 there, so I need 3 in my answer. So final answer will be 28.3 liters, like that, okay? Right, and our final statement, so what is it that we had to find? The volume, okay? So because it's the second one, second volume, you want to call it the final volume. Okay, so the final volume. Okay, and what was it? It was carbon dioxide, yeah. Okay, so the final volume was 28.3 liters for carbon dioxide. Here's the next example. So we have a balloon on top of a mountain here. It occupies a volume of, so we're just going to go through and start writing this out. Okay, so we have a balloon that occupies a volume of 775 milliliters, and the temperature is negative 28 degrees Celsius, and the pressure is 92.5 kilopascals. Okay, so that's at the top of the mountain. Okay, so now we're going to take it and place it at the bottom really quick somehow. So at the bottom, we need to find the pressure. So what pressure at the bottom of the mountain of the same balloon? So again, we're not changing the amount of particles in the balloon. So it has a volume of 825 milliliters and a temperature of 15 degrees Celsius. Okay, so sorry, I changed the temperature and volume so they kind of lined up. And I also converted the degrees Celsius to kelvins, okay? All right, so we have our initial information here, and we have our final information here. Okay, so in the end, we need to find our final pressure. Okay, so that's the required info, okay? All right, so here is what's our plan here. Okay, so our plan is to use our combined gas law equation. Okay, like that. Okay, and remember, I know to use this one because we know that the amount, which is n, right, is constant. So that means, like, I have a balloon, right? I have the gas in the balloon, and we're going to assume that the balloon can't leak out the gas. I have that at the top of the mountain, and then I take it down to the bottom of the mountain. So I haven't added any more gas into the balloon. I haven't let any of the gas out of the balloon, so we have a constant amount here, okay? So that's the condition that we're going to use combined gas law with, okay? So again, next day, in a few days, we're going to look at a different law where the amount is changing, okay? All right, so we need to find pressure this time, so I'm going to rearrange the equation. So again, this T goes to the top, because see it's divided, I'm going to multiply it up here. This V goes to the bottom, because right now it's multiplied, I'm going to divide it under, okay? So just rearrange that. So it becomes, okay, so P1, V1, so the temperature at the bottom goes to the top here, okay? And then the B2 comes down to be with the T1. Okay, so just rearrange those. So basically the B2 went down, the T2 went up, everything else is the same. Okay, so from there, let's go through now and plug in our numbers. Okay, so our initial pressure, Okay, at the top of the mountain was 92.5. Our initial volume was, oh, we're going to convert those as well. So convert those to liters by dividing by 1,000. Okay, I knew we forgot something there. Okay, so initial volume is that. And again, if you did forget it, it wouldn't be a big deal here. Okay, it's more, I just want you to get in the habit of converting to liters because you have to be in liters when we move on to the next gas law. All right, second temperature is 288.15 kelvins. Okay, so just kind of, I know you're on your own, you're not listening, so just go through and like say these things out loud so that you get used to the terminology and how to pronounce things and so forth, okay? The initial temperature is 245.15 kelvins, okay, capital K, and the second volume is 0.825 liters. All right, so again, you're going to see that it nicely, oops, no, not that one. The liters will cancel out, the kelvins will cancel out. So that leaves kilopascals, which is the unit for pressure, okay? All right, so just go through and it's a nice, easy lesson here, and you just have to calculate everything correctly, put things in the right spot of the formula, and you're good to go. Okay, so you end up with 102.135, etc., kilopascals. All right, let's look at our significant digits here. So we have 2 here, 3 here, 3, 3, 2 there. Okay, so 2 digits. How do we get 102 to 2 digits? Well, convert it to scientific notation. Okay, 1, 2, 2 spots. Okay, so that's how you get 102 to 2 digits. Okay, all right, but again, if that's stressful, if you left it as 102 kilopascals, I will give you the mark, okay? All right, therefore, the final pressure. So again, make sure the keyword, you're either stating initial or final with whatever it is that you're finding, okay? So just so it's really clear that you understand what you were supposed to find. So the final pressure was 1.0 times 10 to the 2 kilopascals, and don't forget your units as well. Okay, here's our next example. We're drawing a sample of gas into a piston, and yeah, just looking at these different pieces of information here. So again, if you're wondering what a piston is, just because they'll use it a lot in these gas warp problems and so forth, I have a visual pasted in here, but I found a good website. So here's the link. It just shows you a nice visual of how gas works, okay? So, you know, you take your car. So I know a lot of you are probably in your lifetime probably going to move to an electric car and so forth. But for now, like I think most of you are using a gasoline car. So you go to the gas station, get gasoline, fill up your tank. There it is. Okay. And then it moves along to a fuel pump here, into a filter, and into a fuel injector here where it will inject the gas into the piston here, okay? And so like I showed you here on this diagram, there's usually 4 of them. And so yeah, so what's going to happen is the gas will go in. And so if you're looking at the legend here, there's air in there. The gas is the yellow that's going to come in here, okay? And so what's going to happen is that this piston is moving, and then there's pressure that's changing and so forth, and at some point it ignites and so forth, okay? So, and it keeps the piston moving. This is the piston here, moving it up and down and so forth, and yeah, just kind of moving it through. There's supposed to be 4 of them, okay? So you can kind of go through and look it up if you're interested and so forth, okay? And then at some point they let out the exhaust, the waste as well, okay? So we are going to be looking here at this piston, okay? So there's gas in a car being drawn in, and you're going through this process here and so forth, okay? So let's go through and figure out all the information that we're given here. So we have a piston here. The sample of gas in the piston occupies a space of 0.255 liters. The temperature is 25 degrees Celsius. And we want to know what volume it will occupy. So if I change the conditions here, that's what's required. If the new temperature is 80 degrees Celsius. Okay, all right, and it says here that the pressure and the amounts are constant. So P and N are both constant, so they don't change. Okay, so here's our plan. So this is the one formula that we have been working with. Okay, oh, and actually, sorry, before we keep going here, let's convert the temperatures. So 298.15 kilopascals. So again, I just added the 273.15, and we're going to add 80 to this one here. Okay, so 80 to 273.15, and you get that. All right, so we're going to go through here, and so we're trying to get volume here, okay? So again, this is the first volume, first temperature, second volume, second temperature. So what we noticed here is that, what we're told here is that the pressure and the amount is constant. So again, amount isn't involved in this calculation here, but pressure is. And since it's the same, so it's like it has the same number, so what you can do in this case here is you just kind of ignore the pressure in this formula here. So it ends up just being volume over temperature, and the second volume over the second temperature, like that. Okay, so when so you're going to run into problems like that too, where you know, this is constant, so then you can just cancel it out of the combined law equation. Okay, all right, so then that leaves this, so we're just going to rearrange it so that we have it solved for a b of 2. Okay, so we're just going to boot this over here. So since it's divided, I'm going to multiply it on this side and then divide it all by t of 1, and then I get my v of 2 equation, my final volume equation. Okay, so I'm out of space here, so I'll write it over here. So here's the solve step. So my V2 requires the initial volume, the second, the final temperature in kelvins, and I have divided by the initial temperature. Okay, and then nice thing is all the units that I don't need cancel out, and then leaves me with liters. Okay, so 353.15 times 0.22255 divided by temperature at the bottom leaves me with a volume of, etc., in liters. Okay, and our significant digits here, so we have 3 digits here, 1, 2, 3 digits, 3 digits, so we need 3 digits in our answer. So remember the zeros at the beginning don't count, but then we go 1, 2, 3 digits like that. Okay, all right, so that is your final volume. Okay, so the different thing about this problem here was that sometimes if, you know, some parts like temperature are constant or pressure is constant, then you can just kind of cancel them right out of the formula. Okay. Okay, so there we go. All right, here's the next example. Okay, so we have a weather balloon. It's filled with 60 liters of hydrogen gas. Okay, and at sea level, so the pressure is 101.3 kilopascal. So we're going to release this weather balloon here, and it rises 900 meters above the Earth's surface, where the pressure is 90.6 kilopascals. And we need to find the volume, okay, at this new altitude. Okay, so those are the initial, okay, when we're at sea level. we release the balloon up into the air, and now at this new pressure, okay, so again, so at this new pressure here, what's the new volume, okay? And it says, assume that there is no change in temperature or the amount of gas. So the N, which is the amount, and temperature, they're both constant. Okay, all right, my units are good, liters, kilopascals, all right, so that's given. Okay, what we have in red there is what we need to find, required. Okay, so here's our plan. So we're going to use our combined gas law equation. Okay, but again, temperature is constant, so we can just get rid of it. Okay, so it ends up being just a pressure times volume equals pressure times volume equation. All right, and from there we need V2, so I'm going to boot this out of here. So right now it's multiplied, so when I move it, it's going to divide away. Okay, and there's my V2. All right, so let's go through and solve this. So the second volume is found by taking the pressure of the first one and the volume of the first one and dividing by the pressure of the second one. Okay, and that leaves liters, okay? And sig figs, 3, 3, 4, okay, so 3 digits. Okay, so the final volume of the weather balloon is 67.1 liters. Okay, I just want to do one more example here. I think you probably have a good, comfortable idea of what you need to do here, but I always find that every year students always struggle to find temperature answers, okay? And the reason why is its temperature is located at the bottom of the formula here, and it's a bit tricky to get something that's at the bottom, and normally even in math, out of the equation in order to solve it. So, all right, so we're just going to go through and look at that one so you know what to do when you hit those problems today in the homework. So again, just go through and, list off everything that's given and what's required and so forth as usual. So we have it says milliliters here. So we have a volume of oxygen here. Okay, and it's kept at this pressure, so I can tell by kilopascals here. There are other units of pressure out there, but we're just going to stick with kilopascals for now. But just, make your adjustments if you're in another class where they're using like atmospheres or, millimeters of mercury and so forth, okay? Okay, so the oxygen is expanded to a volume of 700 milliliters, and the temperature is going to be adjusted until the pressure is at 101.325 kilopascals. Okay, so we need to calculate the final temperature. Okay, all right, so the usual information is all here. So we have all the variables as well. So our goal is to find the final temperature here. Okay, so here's our plan of attack. We have our usual combined gas law equation. Okay, so again, if you want to look up how they developed this, you can on your own time here. But yeah, it's just after a lot of studying different behaviors of gases and so forth, they were able to develop this formula. Okay, so what we're going to do here is, so again, we need to solve for temperature. temperature's at the bottom. So whenever you have a variable at the bottom of an equation, it's a little tricky to solve for this. And so forth, okay, even in math. So I just want to teach you a little trick here that is allowed, okay? So basically, if you have something that you need to solve that's at the bottom, so like all the other questions we've done, it's either been pressure or volume, and we just rearrange the equation easily. But when we have a variable at the bottom, there's this trick you can use. You can actually just flip these. You can flip this equation and it's still the same. Okay, and as long as you flip both sides, it's okay to do this. All right. So now we have temperature at the top, pressure and volume at the bottom here. Okay. So the 1 and 2s are all still in the same spots. All right. So now that we've flipped them both, now we can solve for the second temperature. So we're going to move both of these over here. Okay. So maybe I'll use a different color here. Okay, so we're going to move both of these over here because see how it's divided right now? So we're going to multiply it over. Okay, so that means T1 is now going to have pressure 2 and volume 2 beside it. And then we have pressure 1, volume 1, all equal to the second temperature. Okay, so just learn this little trick. If you ever have to find temperature, just flip the whole combined gas law equation up. Like upside down, I guess. And and as long as you do it on both sides, it's okay to do that, okay? All right, so now we have our plan of attack here. Let's go through and add everything in. I'm just gonna do it over here so I don't have to keep scrolling up and down here. Okay, so the second temperature, the final temperature, is found by taking the initial temperature, which we have to convert to kelvins. Okay, so again, we're gonna add 273.15, so we get 294.15 kelvins, okay? All right, so we're going to take our initial temperature and our second pressure reading and our second volume reading. Oops, again, got to change those to liters. Okay, so again, you're just dividing by 1,000. So you get 0.100 liters. So if you take 5 times 10 to the 2, which is just 500, and you divide, so again, this is the same as being just 500 milliliters. Okay, so they just want it to be fancy, right in scientific notation. Keep it to 2 digits. So anyway, when you divide that, you're going to get 0.50 liters like that. Okay. All right, so we're going to multiply the second volume here and divide it all by the first pressure, the initial pressure, and the initial volume. Okay, so let's go through, calculate that out. And again, if you you're just tired one day and you can't remember what the units for temperature are, you can go through once you stack all these up and then just cancel out the same ones, right? Kilopascal, liters. Oh yeah, temperature should be kelvins. Okay, and the answer we got here is something like that. Okay, we're going to go look at our significant digits here. 2, 3, 6 of those, 3. Okay, so anyway, the lowest number is 2. So we need to have only 2 digits here in our answer. So 3.3 times 10 to the 2 kelvins. Okay, so again, I'll accept this, but if you want to practice your significant digits here, that's what you need to do. Okay, all right, so here's our therefore statement. So we are looking at oxygen here. So the final temperature of oxygen is 3.3 times 10 to the 2 kelvins. Okay, and also, so that takes us through all the kind of the different examples, I guess. I guess there's ones where you can you have to find the initial temperature and pressure. We've been finding a lot of final temperature, pressure, volumes. So again, just be ready for that. Just make sure put everything into the right spots in the formula, and then you can go back and solve for one of these and so forth. Okay. All right. So it's straightforward. It's just about being organized with your work and organized with what you're jotting down and putting things in the right spots, solving things properly. Writing the units, writing the final statements, and yeah, and then you should do really well today. Okay. All right. So just practice a few more of those. Again, don't forget to do the conversions. I kept forgetting all the way through. So just get your temperatures to kelvins, get your volume to liters, get your pressure. Well, your pressures should be in kilopascals. If I might have some on the worksheet where it's a different unit. That's fine. Just use whatever unit that there is. In the end, it doesn't matter. It doesn't really matter what units you do have here because they will cancel out. It's just the temperature needs to be in kelvins, okay? But I'm just trying to get you guys to work in liters because next gas law that we learn, we have to be working in liters and kilopascals and stuff like that. So again, just I want you to kind of get comfortable with these, like having to see these units so that if you don't see them, you know you're doing something wrong, okay? All right, go and yeah, practice and try the checkpoint.